Okay, good morning to everyone. For those who did not attend it yesterday, I'm Livorno. I'm a member of H SAF Precipitation cluster, and today I want to talk about the characterization and monitoring of heavy precipitation events in the Mediterranean area using H SAF products and satellite observation. First of all, okay. First of all, I want to thank my colleagues of Institute of Atmospheric and Climate Science of National Research Council of Italy here in Rome for the help and the collaboration. The Mediterranean area is recognized as a climate hotspot, and it experiences a lot of interaction and feedbacks between oceanic, hydrological, and atmospheric processes. And the understanding of this processing is very, very important to also for the environmental and the socio-economic prosperity of the region. In the Mediterranean, often the extreme events originate offshore and are difficult to monitor from ground-based instruments. So the improving given by multi-mission Earth observation the technology provides a unique potential to observe, monitoring, and also understand some physical processes and microphysical processes like the precipitation. So in the use of passive microwave radiometers on board of LEO satellites, few years ago there was the launch of NASA JAXA core observatory in the frame of GPM mission, the Global Precipitation Measurement Mission, to support and integrate the microwave observation from the GPM constellation. So the GPM mission, very quickly, it's composite of 12 LEO satellites, low orbit observation satellites, with 6 different radiometers. The co-observation of the GPM mission brings the most advanced radiometer, the GMI, and for the first time a dual frequency precipitation radar. So the first time we have an active with the KA and KU band radar, an active microwave sensor on board of LEO satellite. The GMI has 13 sensing channels ranging from 10 to 183 gigahertz with the highest spatial resolution available at the moment, ranging from 5 to 30 kilometers, depending on the frequency of the channel. So the HSAF products are, most of the HSAF products are based on the GPM satellite constellation. They are based on two main principles. One is the exploitation of the current and the future the EPS second generation satellite passive microwave radiometers. These are the microwave-based products and also both the level 2 instantaneous precipitation products and the level 3 gridded products. And the second set of products of SAF products combines the information, the estimate from microwave sensors on board of LEO satellite with the infrared observation from geostationary satellite like MSG and MTG in the next future, to provide the near-time precipitation monitoring and estimation, And the advantage is that this set of products combines the physical robustness of microwave observation with very high spatial and temporal resolution of infrared information. On this presentation, we'll focus on these two categories of H SAF products for some case studies, but not only, we also have a look of ground data and also of active and passive microwave raw data, let's say the level 1 data. So we start with the flash flood occurred in Livorno city in Tuscany between 9 and 10 September 2017. Here we have we can see the GMI overpass on September 10th and 1:17 UTC. You can see the retrieval of the precipitation system from the three different channels, the 37 GHz channels, the 89 and 166 channel, and you can extrapolate different information from this channel. From 37 GHz, you can see a depression of the brightness temperature over land, which means very deep convection, and the depression at 89 and 166 gigahertz give an indication of the quantity of ice that we can find in this precipitation system. The H SAF level 2 products can give an idea of how we can monitor the evolution of the precipitation. So we have the estimation of the precipitation rate of three different overpasses with three different sensors. So we have also three different spatial resolution. We also did a comparison with the rain gauges, taking them as reference, both for all the microwave based available product summarized in the H 67 product, and for the H03 product, which combined the information from microwave and infrared channels. So we can see that in this black box, which is the area where we had the main precipitation, the passive microwave, so the H 67, slightly underestimated the total amount of precipitation, while a better agreement was found with the H03B. But at the same time, H03B overestimated the light precipitation, and the extension of precipitation over the whole year in this plot. And on the right, we can see the time evolution of precipitation rate with the rain gauges, which are the black lines, black histogram. The microwave, IR, so H03 B product, the green lines, and the H67, the red lines. So you can see the different trend of this product and also the different temporal resolution. The second case studies we analyzed is the Medicane Numa, occurred between November 15th and 19th, 2017. So basically 2 months ago, the Livorno flash flood. And first of all, what is a Medicane? A Medicane is a Mediterranean cyclone which presents tropical-like cyclone characteristics for a period of its life. Usually, they can be generated in the late summer and fall season. Here we can see the trajectory of the Medicane reconstructed thanks to ECMWF mean sea level pressure reanalysis data, together with the strokes reported by LINET network. So you can see that the Medicane Numa originated in the Sicily Channel and then moved toward Greece. In the all 4 days between 15 and 19 November, we had 53 passive microwave overpasses, and in the mature phase, which can be estimated between 12 UTC of November 17 and 12 UTC of November 18, we have 15 passive microwave overpasses. Here we can see the evolution of the Medicane, the time evolution of the Medicane, thanks to the level 2 H SAF products. So here we have the information from GMI and MSR2 with the related products. So you can see the evolution of the precipitation band and the moving of the system. In the development phase, we had also very interesting DPR overpasses. So we can compare at the same time the information from passive microwave, so from GMI, and the information from active microwave, the DPR. With the 37 gigahertz channel from GMI, you can see the oversea, you can see the extension of rain bands, which are indicated from this higher brightness temperature with respect to the cold background, which is the sea. And on the other hand, with 89 gigahertz channel, you can extrapolate the convective cores which are present around within the system. At the same time, the information from active microwave sensor, the DPR, can give you a more direct retrieval of the precipitation system, and it's also able, the DPR, to reconstruct the three-dimensional structure of the system. And you can see that along this line, which is basically here, you can see that the information from DPR confirms what we extrapolated from passive microwave information. So we have a lot of convective cores, not very deep, but quite deep, up to 9 or almost 10 kilometers, together with some stratiform precipitation, which is evidenced by bright band. So this is a very useful case to understand how the combination of different information from different sensors can help us to understand the microphysical processes and structure of this system. Okay. We have another GMI overpass during the mature phase, and again, from 37 gigahertz channel, we can see the structure of rain bands, and from 89 gigahertz, we can see that during the mature phase, the convective cores are less intense, we have a lower amount of ice particles. So basically, we have only this core can be recognized as convective one, and also the precipitation estimated from the associated product, the auxiliary product H20, shows a lighter precipitation. So if we compare the information from the GMI with the information from a ground radar located in here in the on the red circle, we can see different information. So from GMI, we can say that this is the heavier core with heavier precipitation, and here where there is a very small depression of brightness temperature, we expect weaker precipitation. But if we see the precipitation rate associated with the radar, ground-based radar measurement, we see the opposite. We see the heavier precipitation here close to the coast, and weaker precipitation close offshore. But if we go inside the measurement from the ground-based radar, we see that because of the geometry scan of the radar, we are investigating different levels of the two cores. In fact, we see that we are investigating a lower altitude of the first core and higher altitude of the second core, the core offshore. So this is a clear indication that a quality check of the reference data is necessary also to validate the information that we have from satellite information. Another case study, very interesting, was the Vaia cyclone occurred on the 29 October 2018. This is a very deep depression with the minimum sea level pressure at 978 hectopascal. So we had a strong gradient, a very strong wind, causing damages and casualties. So the most you can see here in the northeastern Alps, we have a huge amount of fallen trees, other than floods and a lot of damages all over the country. So the rain gauges register the very high amount of precipitation, and basically more than 50 rain gauges registered peaks of precipitation in 24 hours between 200 and 300 millimeters, and the Linet network registered more than 530,000 strokes in 24 hours. Again, the time evolution of the system was monitored by the level 2 SAF products. So you can see the origination of the system offshore between the Corsica and Tuscany, and then the development of the system, and it's moving from west toward east during the whole day. And also the level 2 products were used as input for the level 3 H67 product, which give a whole overview of the system in the 24 hours. Here we have the number of alpha hours covered by at least one satellite. So we had up to 16, 17 overpasses in 24 hours in some areas, and this is the total amount of precipitation estimated from passive microwave sensors in 24 hours. We had peak up to 250 millimeter which is a very huge amount of rain if you consider that the resolution of age 67 is 0.25 by 0.25 degrees. On the other hand, the PIN severe product, the H03B product, can be used to monitor the evolution of the event with a very high temporal and spatial resolution. Here we see the evolution of the system between 1:30 p.m. and 11:45 p.m. UTC of 29 October. We did a bit of validation also for this event. So we compared the precipitation amount estimated by both age 67 and age 03B with the precipitation amount measured by rain gauges. And how you can see that the green circle shows a good agreement between the satellite products and rain gauges, while the red and the violet, the purple circles, shows a poor agreement. And we focused on this area around the purple circle, and we divided the whole area in the smaller boxes named with A, B, C, D, E, and we compared the HSAF products with rain gauges, but not only, also the NASA products, always satellite products, of course, GPRAF and iMerge, with the rain gauges. You can see that the HSAF shows a good agreement for the boxes D and E with the rain gauges, especially age 67, and poor agreement for the boxes A, B, C. The situation for the NASA products, it's not even better than the HSAF, showing a poor agreement also for the boxes D and E. If we concentrate on the boxes, on the box E, we can show here we can see the evolution of precipitation rate on the top panel on the right, and the evolution of precipitation amount on the bottom. And at the end, the HSAF products, the yellow and black lines, are in very good agreement with the rain gauges, the blue line, while the NASA products had poor agreement. Anyway, the agreement decreases when we move to box B, as you can see, but it is still acceptable for some of the products, and it's very, very bad for the box A. And this can be related to the fact that the box A and B are mountain regions, so we know that the satellite products have higher difficulties in estimating the orographic precipitation rate. Getting closer to nowadays, we investigated also the Medicane lanos, which occurred in the Mediterranean between 14 and 20 September 2020. We reconstruct the trajectory of the Medicane always with the ECM mean sea level pressure data from the reanalysis, and we also show the linear strokes within a 200 kilometers radius from the minimum of the sea level pressure within 1 hour with respect to each dot that you can see here. So on the right, you can see the evolution of the strokes as registered by linear network, And you can see that this is concentrated around the mature phase, and you can see that there is a period here, roughly between 6 p.m. UTC of September 17 and 6 a.m. UTC of this September 18, where there is no production of strokes, and this can be related to the mature phase of the Medicane. Again, the satellite overpasses can give an idea of the evolution of the system, and here we show the brightness temperature at 89 gigahertz channel with the linear the strokes registered by linear which are the purple crosses. So you can see the 89 gigahertz give an idea of the convective force as we seen in the previous slide, and you can see basically the strokes overlaps this convective course. Really interesting is this image on 22-28 UTC of September 17, where you can see a depression of TB at 89 gigahertz, but basically you don't see any strokes here. So at this point, it's very useful. The first overpasses of DPR during the mature phase of Medicane. We can see the reflectivity at the near surface level, the KU band reflectivity. The near surface level is the level, the first beam not affected by ground clutter, and you can see the well-defined eye of the Medicane, and also the rain bands. Okay, this is reflectivity, but it's the same for the rain rate. Here you can see the altitude, the height of the maximum reflectivity at KU band, from which you can extrapolate information of the property of the precipitation. In fact, here we can overpose this figure, which tell us what are the convective, what are the spectrum pixels as classified by DPR algorithm. So you can see that during the mature phase, the convective pixels are not so much with respect to the spectrum pixel. And at right of this panel, you can see the storm top height, which gives has some information about the vertical width of the clouds. So the information from the DPR tell us that what we have seen here, so the depression of TB, it's not related to the presence of ice, but it's basically related to the presence of supercooled drops, so drops which are at a liquid phase, even if the temperature is well below zero. Again, the information from the two different sensors gives a very useful information about the microphysical structure of the system. We monitor the evolution of the precipitation amount with passive microwave radiometers. So here you can see the evolution of precipitation amount within the whole duration of the Medicane, together with the number of overpasses per day over the considered area. And the same we did with H03B. So here you have, of course, higher temporal and spatial resolution, and you can better monitoring and continuously monitor the evolution of the system. More recently, very recently, We had a flood in Sardinia on 20th November 2020. This is the monitor the evolution of the precipitation of the system with the H product. So you can see that we had a huge amount of rain in 24 hours over northeast Sardinia. We had a lot of damages and also casualties. And during this month, the first part of this month, we had a very long-lasting rain snow event. Basically, we occurred more or less over the Italian country and also over the Balkans. So we had a lot of rain and a lot of the snow over Alps, and the passive microwave product H67 can give us an idea of the amount of the precipitation occurred. So to conclude, the constellation of microwave radiometers can be used for the analysis and monitoring of the precipitation, also to distinguish the different features of the system. The H SAF products can be very effective in the characterization and monitoring of the heavy precipitation over the Mediterranean, especially over the sea, where the ground-based instruments cannot cannot estimate the precipitation. And thanks to the GPM constellation, we have an unprecedented temporal sampling of passive microwave radiometers, but some limitation of this instrument have to be taken into account. We are thinking to the orographic precipitation, which is not well recognized by passive microwave sensors. And also the gaps between the passive microwave overpasses, it can affect the daily precipitation estimate. But at the same time, this gap can be filled by the combination of infrared and microwave techniques, which has a very high temporal and spatial resolution. At the same time, the analysis of these severe events can provide to us the potential and the limitation of passive microwave products, and also the reliability of these products. But we do not have to forget to check the quality of ground data taken as a reference when we do any kind of validation. Here you can see, you can find the references of both the analysis of these of two of these case study we showed here, and also the publication related to the augmented description of level 2 HSAF products. If you're interested, you can download them. Thank you for your attention, and again, for more questions and information, you can contact me or visit both the website, HSAF website, or Twitter account.